Welcome back, folks. Our first fundamental law of circuit analysis. There's three. We're getting our first one here. It's going to take us a little while to get the other two, but we'll get there. And then everything comes back to those three laws. If we can make everything come back to those three laws, nothing comes up out of nowhere. I hate when it's just, here's a formula, go do it. That's not acceptable to me. We got to bring it back to these three fundamental laws whenever we possibly can. Okay, so here's our first one, and it's going to relate. How much energy we're using to push some quantity of charge through some material. Okay, and it's Ohm's law. Okay, I'm sure you've heard of it in some of your prereqs, but let's talk about it here a little and pretty briefly. But we have some resistor. Oh, I didn't draw the resistance symbol in the last video. That's a resistor, folks. All that big hunk of material, and we calculated the resistivity and everything. That's the resistor. Okay, it's got some value R, and we're going to have a voltage across it, higher potential energy up here, lower potential energy down here, and that's our voltage. Okay, it's the difference in energy across that resistor, and that's going to create a current. Okay, that's going to cause some movement of charge. And that movement of charge in this case is going to be down. Okay, and sign matters. Pluses and minuses matter. Do you want plus $1,000 or do you want minus $1,000? Because I know which one it feels like happens to me every day. Okay, so I'd rather plus $1,000. Sign matters is really all I'm getting at. Okay, so we got to make sure we get the sign right. We can relate these three things with Ohm's law. Okay, Ohm's law. We can say the voltage is equal to, well, how much current is flowing through it times the resistance. Right now I have these as time varying. They can be constant. For the first half of the course, they're going to be constant, so I'll more often draw those as constants. Right, we can say capital V equals I times R. Okay, so but sign matters. If I take an object and I hold it up high, where's my camera? I hold it up high and I drop it, it's going to flow that way, right? So it's going to move from high potential energy to low potential energy. And that's the direction the current's going to flow. Okay, it's going to flow from high potential energy down to low potential energy. And that's something that I think you've probably learned. It doesn't really have it does have a name, but it doesn't get talked about a lot. So current, and I think we should give it a name. I think we should call it by its name. Current flows from high potential energy to low potential energy. Okay, so it's going from high to low, so from the top to the bottom, and that's how I get that arrow direction. Okay, and this is called the passive sign convention, and that's what I think gets lost a lot. Passive sign convention. We're going to talk about three different passive elements this semester. There's a fourth that's theoretical, trying to make it in a lab, but there's three passive elements: resistors, capacitors, and inductors. Okay, and for those components, this is going to hold. Whichever side has higher potential is going to push current towards the side that has lower potential. Okay, and that's the passive sign convention. I'll abbreviate it, although it's not as common to see it abbreviated, as PSC, passive sign convention. And we're going to have to make sure we follow this one as often as possible. You can flip it around, but you got to do it consistently, and you're going to confuse a lot of people. So it's a convention for a reason, and we're going to try to stick to it. And we are going to stick to it whenever we're working problems. Okay, so even if you take that same resistor and you draw it a different way, and sure, it's a blue resistor. And you say high potential's over there, low potential's over there, and it's some resistor, right? We got the voltage there. Which way is the current going to flow? Okay, hopefully you can answer that question. I'm vamping now to try to give you a second to think about which direction it's going to flow. And in this case, it's going to flow to the right. I'm going to make sure my camera's flipped the right way. It's going to flow that way. Okay, because it's flowing from high potential to low potential. So we might draw it as an arrow out here. Okay, your current's going to flow that way. So even if it's on its side, it's on an angle, it doesn't matter. You got to look at the difference in energy across the resistor, and that's going to give you the direction of current flow. Okay, so let's play with Ohm's law a little bit, because who doesn't like playing with Ohm's law a little bit, and just make sure we can do this. Okay, and we're going to get some labeled voltages in here, which is fun, right? Okay, so we get a resistor that looks like this, and down on this side we have another one. So that's 8 volts, and this is negative 2 volts. Okay, and we have a 1 kilo ohm resistor, and that negative 2 volts can throw you if you're not comfortable with it, but it's just energy that's below whatever point you're calling 0, right? So if I call ground 0 and I hold an object up here, it's going to have positive potential energy. Okay, but if I drop it down there and I go, well, yeah, but the 0 potential energy line was really up here to begin with, then the object on the ground has negative potential energy. It's just below whatever reference level we're using. Okay, what we're interested in here is the voltage across this resistor. So if I have 8 volts here and I have negative 2 volts here, across it, I have the difference between the two, right? So it's going to be 8 minus negative 2, also known as 10 volts, and the resistance in this case is 1 kilo ohm. Okay, then according to Ohm's law, we have 10 volts. Okay, we want to find our current. It's going to be a constant because our voltages are constant, and we have a 1 kilo ohm resistor. Okay, this is where we start talking about putting the K into your calculator. I gotta get a calculator simulator. I have MATLAB, but we'll see about that. Using a calculator would be good too. So if I solve for I, this would be 10 volts divided by 1 kilo ohm. Volts divided by ohms is going to give me amps. Okay, the units work out nicely with Ohm's law as well. But I'm going to enter it in my calculator differently. If I was going to enter this in the calculator, I would enter it as 10, because the calculator doesn't care about units. You have to. Okay, 10 divided by 1 E3. Okay, and hit enter or equals or whatever your calculator does, and it's going to spit out 10 E negative 3. Okay, now you might have been able to do that in your head, and that's fine. This is a really simple problem. We're starting out slow. We're going to build up in complexity. But by entering it in the calculator this way, I can look at this and I can say, hey, let's slide that back up there for the answer, right? And I can say correctly that is 10 milliamps. Okay, so I didn't screw up my SI prefixes because I let the calculator do the thinking for me. And I'm encouraging you to do that, because eventually you'll screw it up. I will make problems that are intended to have you screw it up by making assumptions about the SI prefixes. Okay, so that 10 milliamps is going to flow through this resistor, and again, I'm going to say, which direction does it flow? It's going to flow from high potential to low potential, and that's going to be this way, right? So it's going to be 10 milliamps. Okay, we got that from down here. That's where that value came from. All right, so Ohm's law is good. We got to think about the passive sign convention while we're applying Ohm's law. Okay, so current flows from high potential to low potential. That's probably the most common way to see it described, the passive sign convention. The other way that I see it written is positive current enters the positive terminal. I may say one or both while we're doing live chats during the semester. Positive current enters the positive terminal. Okay, the positive side of the... Ooh, you can't see that. How's that? Positive current enters the positive terminal. There we go. Ooh, I wish I had a little more space in my camera. It's a little tight in here. Okay, so here's the positive current. It's going down, right? And the positive terminal, I have my 10 volts across here, right? It's 10 volts. So the positive going current enters the positive terminal, and then it flows down. So that's the other way that you'll see the passive sign convention discussed when talking about Ohm's law. Okay, so you're going to answer a couple simple Ohm's law web work questions, and then we're going to move on and talk about power dissipation, because power dissipation is, well, everything is about energy in life, isn't it? So we definitely have to talk about how much energy we're using per unit time, and that's coming up next. Okay, so stay tuned and good luck.